Hey everybody, today we will discuss proving the way that we will show that conditioning will always improve the entropy of our random variables. So first let's start by defining what is entropy. So entropy is the sum of the probabilities that we get what we get times the log of those same probabilities. Next, we can define what is mutual information. So mutual information is the information we can get from two dependent variables. Um, and we can define this as the sum over our first random variable times the sum of our second random variable times their joint probability times the log of their KL divergence. And so this here right here is the KL divergence, just showing how two random variables are related and almost like the correlation coefficient of two random variables, but not for the bivariate normal case, which we all know is rho. And so simplifying this, we kind of want to connect how does mutual information connect to the entropy or the conditional entropy of random variables. Um, So what we can do is using the law of conditional probability, we can show that this is p of xy times the log of p of x given y times p of y times p of x over p of y. So here we can cancel p of y, and using log laws, we can um, subtract the numerator here by the denominator, and we get p of xy times the log of p of x given y minus the log of p of x. And now what we can actually do is we can split this double sum over these two logarithmic terms. So now we have the sum of x, the sum of y of p of x comma y times the log base 2 of p of x by y minus the sum over x's minus y's of p of x by y times the log base 2 of p of x. And here, um, here we're summing over all y's of p of x y. So we just, and this has nothing to do with y. And so, and P is a known PMF that should sum to 1. So then we're just left with the sum over x of P of x times log base 2 P of x. And here, this is actually equal to the positive h of x, the entropy of x. And we're going to do something very, very, very similar on this side too. And we're just going to say this is minus the sum of x, sum over y of p of xy times log base 2 of p of x given y. And here, this is actually the conditional entropy of h of x given y. So now this is actually minus h of x given y plus h of x. So therefore, that we actually have our mutual information is just h of x minus h of x given y. So what we did is we just turned mutual information as a kind of expression of probabilities and the forms of their entropies and conditional entropy spelled out into a closed form of just two entropies. So the next thing we will actually want to show is that the mutual information is actually always positive, which means that the entropy of x is always greater than the entropy of x given y. So what we can do is, to prove this, we can kind of say that the negative mutual information should always be less than 0. And we can do that using some tricks in our books. So we can have the negative mutual information of x given y is just the negative double sum of x over y of the joint PMF times the log of the KL divergence. And what we can do is we can bring the negative to the inside of the log and switch the sides from numerator to denominator. So p of x, y is 2 of p of x, p of y over p of x, y. And now we have that this is the same as the as a random variable times a function g over some function of a random variable. This is actually the same as an expectation of some function g of our PMF, which happens to be the log. So this is the expectation of the log base 2 of p of x, p of y over p of x comma y. And now we know x is convex, but log is therefore concave. And if we have an expectation and a concave function, we should know that this will actually always be less than the log of the expectation of this uh, probabilities of random variables. Um, and now we have some expectation of some joint PMF and some probabilities on the inside. We can actually just go back to the double sum. So we can just say this is the sum of x, sum of y, joint PMF, and then our independent PMFs by our joint PMF. And now here we can cancel this, and so we just see log base 2, the sum of x, sum of y, p of x, p of y. And then by independence, this should just be the log of the sum of p of x over all x's times the sum of p of y over all y's, and summing a PMF over all of its x values should equal 1. Summing another PMF over all of its y values should be 1. So this just ends up being the log base 2 of 1, which equals 0. But we have Jensen's here, so this is Jensen's inequality, which says switching expectation and a convex function will always be greater than what it was, or switching an expectation and a concave function will always be less than what it was. So then therefore we have our mutual information, our negative mutual information is always less than 0. So then we have our mutual information is always greater than 0. So therefore we know that actually conditioning on xy makes our entropy less than our conditioning, than no conditioning on just x. And so now we have proven that conditioning actually always ends up reducing entropy. Thank you.